Hello fellow students of Organic Chemistry 2213. Today for Orgo 2213 Connect, I will be going through the process of extracting caffeine from black and green teas for when you really need to stay awake studying for our final date with Professor Workington. Ultimately, what we want to do is extract the caffeine from the brewed tea mixture by dissolving the caffeine into an organic solvent that caffeine will dissolve into more readily than it will into water, and separate that organic layer from the aqueous mixture. After separating out the organic layer, we will then proceed to boil away that organic solvent, which should hopefully leave enough crude caffeine at the bottom of the boiling beaker that we can then proceed to do a recrystallization of that crude caffeine to produce pure caffeine. Well, the first question you're probably gonna ask is, but where do I get my hands on an organic solvent that's readily available? Well, I've got some good news for you. Kinda. Using some very common household products, you can make yourself some trichloromethane, commonly known as chloroform. Alright, time for a disclaimer. 1. Chloroform is carcinogenic. 2. Chloroform is poisonous. While chloroform was once used as an anesthetic, it would take time to render a person unconscious. Fair bit of time, actually. Don't let Hollywood fool you. And it would require, a trained anesthesia person. Do not use this chemical for pranks. You run the risk of poisoning someone, suffocating them, in addition to possible cancer-causing problems. Really puts a dampener on your friendships. Not that I know from experience. So, with that out of the way, one would ask, how does one make chloroform? Well, the easiest way to do that is to perform a haloform reaction in which a methyl ketone is halogenated in a basic environment. So, how do we do this? Well, our easiest and cheapest option is to halogenate acetone in a solution of sodium hypochlorite, also known as, common household bleach. But before we even get to that stage, like any good chemist, we don't want to start slapping chemicals together willy-nilly. Oh no, no. We want to do this the right way. And that means everybody's favorite thing? Stoichiometry! To determine the concentration of sodium hypochlorite in the bleach solution, we're going to do a crude titration by reacting samples of the sodium hypochlorite with another reactant until there is no more observable reaction. As you can see here, there are 4 50 milliliter Erlenmeyer flasks, each filled with 5 milliliters of the sodium hypochlorite solution. Why are there 4, you might ask? Well, because we're scientists, damn it! And if we're going to do an experiment, we're going to do it with replicates. The reactant that was chosen for this crude titration was hydrogen peroxide. It's readily available, can be found at any drugstore or supermarket, and it more often than not has an accessible MSDS with its known concentration, usually in percent weight per volume. As you can see when the camera zooms in, that the reaction creates a large amount of bubbles within the flask, and that is the hydrogen peroxide reacting with the sodium hypochlorite to produce sodium chloride salt, water, and oxygen gas, the formula for which you can see on the screen now. In this instance, I used a disposable pipette to transfer the hydrogen peroxide drop per drop into the individual Erlenmeyer flasks. This was done so I could maintain better control of the drops, and that purchasing burettes is really expensive for a student. While pipetting the hydrogen peroxide into the sodium hypochlorite, make sure to record the volume of hydrogen peroxide that was used in the reaction once the reaction stops visibly, well, reacting. This will be important later. The MSDS for hydrogen peroxide gives its concentration in percent weight per volume, which is described as mass of solute in grams per 100 milliliters of solution. Therefore, if the concentration of hydrogen peroxide is 3% weight per volume, then its concentration is 3 grams per 100 milliliters. And if the molar mass of hydrogen peroxide is 34.01 grams per mole, that equals 0.088 moles per 100 milliliters, or 0.88 moles per liter. And now that our concentration of hydrogen peroxide is in civilized units, we can continue doing our stoichiometry. Using the average volume of hydrogen peroxide used in our flasks for our titrations, we can use the concentration of hydrogen peroxide that we just determined to determine the number of moles of hydrogen peroxide that were reacted during our titration. Using the equation for this reaction, we can see that hydrogen peroxide reacts with sodium hypochlorite in a 1-to-1 ratio. This means that there are 5 times 10 to the power of -3 moles of sodium hypochlorite in each 5 milliliter Erlenmeyer flask. This works out to a nice even 1 mole per liter. Alright, now that we got the stoichiometry out of the way, you're probably thinking, alright, we know the concentration of the sodium hypochlorite now, so we're ready to just mix that with some acetone and make us some chloroform. Well, you'd be wrong, because first off, when you react the two together, it forms an aqueous layer, and the chloroform, the organic solvent, will settle at the bottom of the container. Now, when you separate the organic layer out, you're still going to need to dry it out with a drying agent, because there will still be a little bit of water mixed in with it. So that means first we need to make us a drying agent. And the drying agent we're going to use, because it's relatively easy and cheaper, is magnesium sulfate. Alright, for this, the first thing you're going to want to do is preheat your oven to 100 degrees Celsius. To make our anhydrous magnesium sulfate, we are going to be dehydrating magnesium sulfate heptahydrate, which comes in the common form of Epsom salts. After recording the initial mass of the bag of Epsom salts, you're going to want to spread an even layer of the salts on a clean baking tray until the bottom of the tray is completely covered. Make sure to record the final mass of the bag so that later we can do even more stoichiometry. When your salts are ready, put them in the oven for an hour and leave them to dry. After your salts have been drying for an hour, you're going to want to take them out of the oven and break apart any large chunks that you find and gently shake the tray to evenly distribute the salts across the tray, and put it back in the oven for another hour at 150 degrees Celsius. After your salts have been in the oven for an hour at 150 degrees Celsius, you're going to want to once again take them out, break apart any large chunks, and then shake the tray to evenly distribute the salts across the tray. And put it back in the oven, this time for another hour at 250 degrees Celsius. After being in the oven for an hour at 250 degrees Celsius, you're going to once again take out the tray, break up the large chunks, and shake it again to evenly distribute it. At this point, if your oven goes up to 310 degrees Celsius, you're going to want to put the tray in for another hour. However, my oven does not, therefore, well, I didn't. After recording the mass of a clean, dry container, you're going to want to take a clean, dry mortar and pestle and grind up any chunks of the now supposedly anhydrous magnesium sulfate into a fine powder. So the reason for this gradual heating is that the magnesium sulfate heptahydrate doesn't release all of the water molecules from its crystal structure in one go. And the gradual heating prevents the magnesium sulfate from burning and decomposing into magnesium oxide and sulfur trioxide. Also, that's sulfur with a pH, not an F, like some sort of barbarian. At 105 degrees Celsius, the heptahydrate gets dehydrated to a trihydrate. At 150 degrees Celsius, the trihydrate is further dehydrated into a monohydrate. And finally, the last water molecule in the crystal structure of the monohydrate is finally liberated at 310 degrees Celsius, which my oven could not reach. Alright, time for more stoichiometry. The total mass of heptahydrate that was used was 483 grams. Now, using the molar mass of 246.47 grams per mole, is able to determine that there is 1.96 moles of heptahydrate. This means that in a 1-to-1 ratio, there should be 1.96 moles of anhydrous magnesium sulfate at the end of the dehydration. Using the number of moles and the molar mass of 120.37 grams per mole, molar mass of anhydrous magnesium sulfate, I determined the theoretical mass that I should have gotten to be 235.88 grams. Unfortunately, I got 283 grams. This means that my final product is definitely not pure and definitely not completely dehydrated. However, using the molar mass of the monohydrate, my theoretical mass is much closer to my final mass. From this, I can pretty much determine that it's an impure mixture, but probably mostly of monohydrate. Alright, with all of that finally out of the way, now we should be ready to make the chloroform, right? Right. We're good to go. Now it's time for the haloform reaction. And here is the reaction mechanism for the haloform reaction of sodium hypochlorite and acetone in solution. I won't be going through the entire mechanism, but keep in mind that the reaction is made possible by the dissociation of the sodium hypochlorite into a sodium cation and a hypochlorite anion in the solution. The dissociation of these ions in the water allows for the creation of OH negative ions, which are what drive the reaction forward. On a side note, this reaction is relatively exothermic, so it would be beneficial to properly cool your bleach to about 5 degrees Celsius. Or, if you're in a rush and you don't want to wait for your bleach to cool, you can also put the beaker that you're going to do your reaction in an ice bath. After packing the beaker in ice, I poured 900 milliliters of the bleach of the concentration that we determined earlier. Next, I slowly added 100% volume per volume concentration acetone to the sodium hypochlorite solution. I continued adding the acetone until the sodium hypochlorite solution turned a white-ish colorless color. This color change can be used like a crude titration point. The cloudiness you see is the droplets of chloroform suspended in the aqueous solution. After letting the mixture sit for several hours, the chloroform will settle to the bottom and form an organic layer. At this point, you will want to carefully decant off as much of the aqueous layer as possible. I then used an eyedropper to carefully collect as much of the organic layer remaining in the beaker as possible. However, if you feel like being some sort of fancy schmancy newfangled chemist, you could use one of them, separatory funnels to save time. Unfortunately, yield was low due to the relative concentration of bleach compared to acetone. After a few batches, I acquired enough crude chloroform to do the extraction. After dehydrating using magnesium sulfate monohydrate, the crude chloroform was gravity filtered and collected. The total volume of sodium hypochlorite that I used to create the chloroform was 3.6 liters. 3.6 liters at 1 mole per liter gives a total of 3.6 moles of sodium hypochlorite that were reacted. As you can see from the equation shown, 3 moles of sodium hypochlorite react with 1 mole of acetone to create 1 mole of chloroform. Therefore, the theoretical number of moles of chloroform that were synthesized should be 1.2 moles. Using the molar mass of 119.38 grams per mole, I calculated the theoretical yield of chloroform to be 143.26 grams. Using the experimental yield and the theoretical yield, I calculated the percent yield of chloroform at 37%. Now, with all of that out of the way, we're ready to do our extraction. To prepare the green tea solution, I first measured out 10 grams of green tea leaves. I then added 250 milliliters of distilled water and then put the beaker on a hot plate to boil. Not seen on camera is me adding 12 grams of sodium bicarbonate to the solution to allow the polyphenols that are also present in the tea solution to form water-soluble salts. After boiling for 10 minutes, the green tea extract was repeatedly gravity filtered to remove any debris from the mixture. After a thorough hand washing, a soft cat was pet. This is a very important step and must not be forgotten. While waiting on the gravity filtration of the green tea solution, the black tea solution was made with 10 grams of black tea, 12 grams of sodium bicarbonate, and 250 milliliters of distilled water. The black tea mixture was then put on to boil for 10 minutes. The black tea mixture, like the green tea mixture, was repeatedly filtered via gravity filtration. After each gravity filtration, the filters were pressed to extract as much of the tea mixture as possible. In the absence of a proper separatory funnel, the 3 7-milliliter washes of chloroform were done using a series of beakers in which the chloroform and tea mixture was gently swirled to prevent the creation of an emulsion. The chloroform layer containing the dissolved caffeine was collected using an eyedropper after each wash. Once all 3 washes for the green tea mixture were done, the chloroform caffeine mixture was dried using magnesium sulfate monohydrate. The chlorine caffeine mixture was then filtered using gravity filtration. Following the same procedure used on the green tea mixture, the black tea mixture was washed 3 times using 3 washes of 7 milliliters of chloroform each. The chloroform caffeine mixture was then collected using an eyedropper, dried using magnesium sulfate monohydrate, and then gravity filtered. The gravity-filtered chloroform caffeine mixtures for both the green and black teas were put on a hot plate and the chloroform boiled away, leaving a caffeine residue. Were I a good chemist, and I'm not, I'd try to recrystallize these, but the yield was so low that I don't think I'd get anything out of it. And there you have it. Extraction of caffeine in a home laboratory, potentially exposing yourself to carcinogenic chemicals and making other bad decisions. Good luck. Keep up with Orgo 2213 Connect.